Welcome to the Gin and Tonic show on this February, the 17th of February, 2017. That's a fortuitous number. It's Rob, and we're back after me being away for a week and some of the other guys hosting. So thanks to Abu and Ike and Stops, etc., for filling in for me. We'll just wait for a couple of people to join the Hangout so we can have a lively chat. For some reason, my program called ManyCam is not working. I wanted to play a short video that I'd edited down that we could discuss this evening, but for some reason, it's just not sending the signal through. Good evening, guys. I'm here, so feel free to join. I will repost the link again. Hopefully it's working. I'll copy it and paste it in there again into the chat. There you go. So just check that for me and tell me if you are able to join the Hangout with that link. It should let you in. Here's the video that I actually wanted to play. And as I say, for some reason, that video is the software which I use is called ManyCam, which sends a signal through. It does not work. Okay, no problem. Let me just give you the link again then. For some reason it's not working, Abu says, so I'm going to just copy and paste it again. Try this one here. See if that one works. Try that again for me there, Abu. I don't know why it keeps changing. I copy and paste this link in there each time, and for some reason it keeps changing. So I don't know. I know what it is. I know what it is. I think it gives you a unique link every single time you start the webinar. So even if I go in and attempt to start it, the next time I go and do it, the link must change. So hopefully that'll work for you now. There we go. GP, good evening, sir. How are you? There we go. There we go. We've got a few people in there. Hey guys, are you on? Can you hear me okay?
Yes. But I've got to sort out some changes I've made to the computer.
Okay. Yeah, for some reason, the ManyCam program that I use here to be able to play videos is just not sending a signal at the moment. I've got it all live here, but...
I have a question. Yeah, this ManyCam, is this something you paid for to have for Google?
Yes, yeah, I paid for it. It's called ManyCam, M-A-N-Y Cam, C-A-M. It's basically a live switching.
That's very good because the thing is, I prepared a little presentation for my quantum mechanics argument. So I wanted to show a short presentation on a video, but maybe I can just post the link in the
yeah, because from what
chat.
I can see, when you try and do it through Google Hangouts without using ManyCam or something, you don't get any audio. That's been the problem. Or if you've got to unplug your headphones, and so you've got to let the mic on your computer.
I have prepared for that, but I just thought that it's more.
Okay, cool.
If it works.
Yeah, yeah. We're happy to do that. So do you want to start off and go ahead and do that?
Yeah, maybe that's best to start with it. It might be long, but can you try to? You can just try, see if you can play this video as a test.
You want me to play it? Yeah.
Yeah, test if you can play it. Otherwise, we do it the Stone Age method.
Well, I mean, I can certainly play it, but I don't think it's going to have sound because I'm using headphones.
You're not using. Okay, but then I do it. Okay, then I play it. I guess just as a test if this mini.
Yeah, just because the family's home, and so I haven't found a way where I can play through the headphones now. As I say, for some reason.
But I play it. We'll see how this works.
And so on. And so on the back screen, you end up with what's called an interference pattern, a series of light and dark fringes where waves have either cancelled out or worked together in phase. That's fine. That's not quantum mechanics. That's a property of light that goes back over 200 years that we've known about since the early 19th century. Imagine doing the same experiment again, but doing it not with waves, but with particles. With grains of sand. So this is the same experiment, but I've tipped it 90 degrees. Rather than waves that are spread out that wash up against the two slits and squeeze through, here you've got individual particles of sand, and each particle will either go through one slit or the other. And so you see they will sort of drain through, and you get two bumps underneath each of the slits. So the two peaks is reminiscent of particle-like behavior, whereas the multiple pattern of interference is wave-like behavior. What if we do the same experiment with atoms? Well, so imagine we have an atom gun, something can fire atoms, a stream of atoms. You can't see them because they're very small. Let's block off one of the two slits. So these two slits are you know, the dimensions and separation of the slits is chosen appropriately to show us how atoms do things. And so far, so good. Nothing strange here. You'll see a lot of atoms hitting the back screen. So this will now have to be some sort of photosensitive screen whereby when an atom hits it, it'll give off a little flash of light to say the atom has arrived here. So the atoms are arriving as these little pinpricks of light that we see. Of course, a lot of the atoms will be blocked by the first screen. They won't go through that slit. But those that do get through to the other side, you can see there's a bit of spreading of the atoms. But if we didn't know anything about atoms, we say, well, that's fine, we can understand that. A lot of the atoms are going clean through the slit. Some are sort of maybe bouncing off the edge of the slit, and so they're sort of being deflected a bit, which is why you get a bit of a spread. The first mystery of quantum mechanics comes when we open the second slit. Because now we see something that's very much like the interference pattern we got with light. Rather than having two bands of spots where the atoms have gone through the two slits, it's as though the atoms have gone through the slits behaving like waves, and you get interference of the waves, and you get these bands. If we know nothing about atoms or quantum mechanics, you could try and rationalize it and say, well, you know, maybe atoms behave in a very strange way, and only a certain number of them are allowed to all sit together. And so, you know, me and my gang, we're all going to go on this slit. No, sorry, no room for you. You go the next slit above. And by the way, there's this rule that no one can go in between the two bands, but a few naughty atoms do. So there's a bit of a scatter. You know, we don't. There could be some forces between atoms that make them coordinate their actions in a way to give this pattern. That's not mysterious. That's just, we just don't know how atoms do things. But we can be clever, and we can force the issue. What if we were to not send the atoms all through at once, but send them through one at a time? Leave enough of a gap for the atom to get through to hit the screen. Of course, as I say, some atoms will hit the first screen and not get through, but those that get through will hit the back screen. So let's run the experiment again slowly, and gradually you'll see as the atoms go through, they'll look like they're just randomly arriving on the other side. You keep sending atoms through one at a time, and gradually that same pattern appears. So each atom by itself is somehow contributing its small part to the overall wave-like behavior that we see in the interference pattern. How does it do it? How does, we know the atom's a tiny localized particle, we can't see it, it's too small to even see under a microscope, we're firing it at the screen with the two slits. Some moment later, you see a flash of light on the back screen. It's arrived in a localized point, it's not spread itself out. You don't get sort of like a wash of a faint light across the whole screen. It's a little point. The atom is localized, it's arrived in a certain location. And yet, it somehow seems to have been aware of there being two slits, not one, because it's given rise to this interference pattern. How does one atom do that? Does it split in half? Does it become like a cloud that goes through both? Well, we can try and be even cleverer. What if we were to spy on the atom and see where it goes? We can gently just observe which slit it goes through. So you put a detector just above the upper slit that will flash or beep whenever it sees an atom go through that top slit. Sure enough, you fire the atoms through one at a time. 50% of the time, the detector will beep. The other 50% of the time it doesn't, the assumption being that the atom has gone through the lower slit. But of course, I've been cheeky here. I haven't shown you the results of the experiment. That's what you get. 50% of the time, it beeps, and you see a spot arrive adjacent to the upper slit. The other half of the time, it doesn't beep, but you see a spot arrive at the lower slit. So, yeah, it's picked out the atoms that have gone through the upper slit and not the ones that have gone through. So each atom does go through one slit or the other. But that's a different result to what we had earlier. So here's the last bit of sneakiness that we can play with atoms. Surely now, you know, we're going to get to grips with it. Leave the detector there, but just very quietly go and unplug it. Don't let the atoms know that you're not spying on them. Make them think that you're still detecting them. So, yeah, okay, we're going to run the experiment, atoms. Okay, get ready, one at a time. We're going to be checking on you. All right, so run the experiment again. Now, if you can explain this using common sense and logic, do let me know, because there's a Nobel Prize for you.
Okay. Are you still there? Guys?
I'm sorry, I fell asleep.
Did you fall asleep?
Yeah, I'm still here. I've watched this man talk before, and I sometimes wonder if he's made a mistake at the end.
A mistake? What do you mean mistake?
Because there's different videos which say the opposite to what he says at the end by various scientists. Some say it, if you leave the camera on, it doesn't show it, and does show it, and others say it doesn't show it, but it does. Like
this is how it works. Again, if you want me, I can show a video where I show the actual experiment. Okay, anyway, let me just take this, otherwise.
But I use this as a theory to prove that God doesn't exist.
Okay.
Well, an all-knowing God is the camera.
Let me just take my presentation, and then we can, because this is how the experiment goes. And there are very many different like versions of the double slit experiment. This is not the only one. There are many more high-tech versions of this. This is just most famous. Okay. First, I want to say something about intuition. I would say that our intuition is similar to our vision. As we all know, we can only see a tiny part of the electromagnetic spectrum. More specifically, we can only see electromagnetic waves with a wavelength between 380 nanometers and 700 nanometers. However, electromagnetic waves can have wavelengths over 1,000 meters, like in long radio waves, and smaller than 0.1 nanometers, like in gamma waves. Evolution by natural selection has fine-tuned our vision to see light with a wavelength between 380 nanometers to 700 nanometers, but evolution did not fine-tune our vision so that we can see wavelengths longer or shorter than this tiny span of the electromagnetic spectrum. Evolution by natural selection has fine-tuned our intuition to a similar tiny spectrum. Our intuition understands things like picking bananas from trees, having sex with fertile members of the opposite sex, and hitting each other in the head with sticks. Our intuition is fine-tuned to this tiny spectrum of reality that was necessary for our survival on the African savanna. However, when Einstein showed us that space and time is one geometry, that space can stretch and bend, that time can be slowed down by massive objects, etc., our intuition is completely useless, as we would expect if evolution by natural selection is true. The same thing happens when we are studying the really small. How can an electron be in more than one place at once? It makes absolutely no sense for our intuition. Okay, keep that in mind. Why should we care at all what interpretation of quantum mechanics is the correct one? Well, quantum mechanics is probably the best theory that science has ever produced. No theory has been more empirically tested than quantum mechanics. Yet the old school textbook quantum mechanics is either logically inconsistent or incomplete. The old school book says, 1. All isolated systems evolve according to the Schrödinger equation. I have a nice my pictures. Anyway, all isolated systems evolve according to the Schrödinger equation. 2. When a system is observed, its wave function collapses in a random way, meaning when they are observed, they do not evolve according to Schrödinger equation. To visualize the inconsistency, let's do a Gedanken experiment. So, to visualize, if we take the Andromeda galaxy and remove all stuff, including photons, dark energy, etc., within a buffer around it, and maybe Donald Trump builds a 3-dimensional wall around it, so that it becomes a completely isolated system. According to axiom 1, the Andromeda galaxy now should evolve according to the Schrödinger equation. Okay, fine, all is hunky-dory. But now imagine that life has evolved on some planet in the Andromeda galaxy, so that we have an observer that is doing an experiment, say the double slit experiment. The result of that, according to the axiom 2, the system does no longer evolve according to the Schrödinger equation. What Everett did was simply to get rid of axiom 2. When a system is observed, its wave function collapses in a random way, meaning that there is no collapse of the wave function. The wave function continues. We are thus left with one axiom: all systems evolve according to the Schrödinger equation. The only thing we have to do now is to study the math, and we will predict what's going to happen. And when you do study the math, you will find that it will appear for different observers in the system as if the wave function collapses. However, quantum decoherence can explain why we cannot see all the different layers of the system. Okay, let's take a step back and consider this. To verify effective hypotheses, we want to understand what reality is. Okay, like 1. External reality hypothesis. There exists an external physical reality completely independent of us humans. Why would the Andromeda galaxy stop existing if all life on Earth died tomorrow? 2. No secret source hypothesis. We are our particles. Consciousness does not require any secret source, like if there was some kind of spirit field that can collapse the wave function. I'm not a dualist. Okay, you might say, stop, Abu. I know the answer, and that is that quantum mechanics only applies to small things and not to the big bad world we are living in. Well, we can actually not confine the quantum weirdness to small particles like electrons and photons. For the first, before I say anything else, scientists have actually shown that if you can isolate larger molecules in the same way as you can isolate electrons, the big molecules behave quantum mechanically as well. And by the way, we are made of those particles. The most famous Gedanken experiment that deals with this problem is Schrödinger's cat. Okay, show a little picture here. There. Which is an example of an amplification process where microscopic weirdness is amplified into macroscopic weirdness. Whether one atom has decayed or not decides if an entire cat is dead or alive. And in fact, nature is full of those things. Chaos theory is all about how tiny differences in initial conditions gets amplified to macroscopic differences, and whenever you have no linear chaotic dynamics, this happens. Our brain has chaotic dynamics like this, so what individual synapses can do in our brain can cause major differences in our behavior, etc. The world is simply full of it. Let's now jump to cosmology. Our best theory of how our universe evolved is the inflation theory. This theory predicts a lot of things like space, like that space should be flat, which it is. There should be fluctuations in the density field, and they should be almost completely scale invariant, which these fluctuations are proven to be, and a lot of the other things that it predicts. One thing it predicts is that space is not big, but infinite. Andre Linde and others shows that inflation generally uses a truly infinite volume of space, which by the way gives us another kind of multiverse, but not in Hilbert space like Everett's theory, but in other places in what we normally call space. The product of this is that different versions of you exist even in Everett's theory, even if Everett's theory is wrong. If you want a longer, I can talk long about this. Anyway, so if your only argument against Everett's theory is that you reject the idea of countless copies and versions of yourself, well, I'm sorry, you'll get that from Linde's inflationary cosmology as well. So if we talk about some arguments / worries against Everett's adaptation, the Occam's worry. Parallel universes feel wasteful. If you're worried about complexity, then you're lost anyway. The entropy of our visible universe is about 10 to the power 89 bits. Yes, a lot of complexity is created if the wave function never collapses, but that complexity ultimately springs from a simple equation, the Schrödinger equation. I would like to use Occam's razor against the enemies of Everett. All the other interpretations, as far as I'm aware of, need some extra ad hoc hypothesis to explain away the wave function. Thus, Everett's many-world interpretation actually is less wasteful, since all what it does is accepting the theory for what it is and following it to its logical conclusion without any extra ingredients. A bigger reality may be bigger, but it can also be simpler. Equal probability worry. How to derive probabilities from causal theory. Imagine that you will be put to sleep and cloned. One copy of you will wake up in room 1 and one copy will wake up in room 0. Subjectively, it will feel for both of them that they randomly woke up in a particular room, but in reality, it was not random. This is the same problem in an infinitely inflating universe. Why did we wake up in this universe? Was it random? No, but it feels subjectively random for us. Unequal probability worry. Some things are more probable than others, meaning that more branches of the universe will end up in a certain position than others, even if all of them happens, although not equally frequently. This is just the nature of quantum mechanics. If you don't like it, you can beep off. Invisibility worry. Why can't we detect all parallel worlds? Why don't we see things in superposition? Well, because of decoherence, dude. Wait a minute. Now I'm going to show you this nice video. In the background, yes. Decoherence. It's like a bit like saying, why can I only listen to one radio frequency at once? If there really are many different radio frequencies passing by simultaneously, why can I only tune the radio to one of them at a time? Unless we figure out a way to jump from one branch to another and then back again, we can not communicate with branches of the universe that have decohered from our branch. We can tune into a different radio frequency and back again, but I don't think we'll be able to do the same with different parallel universes, at least not in my lifetime, although it would be cool to do so. Word worry. Some smart asses define exists as something that we can observe, which would mean that things outside the boundary of our like visible universe from which light has didn't have time to reach us, those part of the universe therefore does not exist. This is absurd. Why would existence care whether we can observe it or not? 3 kinds of philosophical villains. Omnivision assumption. Physical reality must be such that at least one observer can in principle observe it all. A bit like an ostrich with his head in the sand, saying that what he cannot see does not exist. This is an anti-Copernican view and a very hubristic view that thinks that humans are so important that the universe must function in such a way that it is possible for us to observe all of existence. I do not think the universe/multiverse give a damn about whether or not we can observe anything in it at all. Pedagogical reality assumption. Physical reality must be such that all reasonably informed human observers feel that they intuitively understand it. If a theory feels weird to a human primate, this theory must therefore be wrong. So when we start to investigate things that travels much faster than, and we find that time slows down, that's not very intuitive and pretty weird. We investigate massive objects like black holes, and we found that they are very non-intuitive and weird. We investigate things that are smaller than the human scale, and we saw that particles can be in multiple places at once. That is pretty counterintuitive and weird. Much colder than humans are used to, like when liquid helium flowing upward. That is weird. Much hotter than humans are adapted for, like high energy collisions, like protons at the Large Hadron Collider, and we get things like the Higgs boson, which is as intuitive like colliding a Volvo and a Volkswagen, and out pops a cruise ship. Cruise ship and a fighter jet. This is what we should expect to find, because our brain did not evolve to understand things outside our scale. Whatever the true interpretation of quantum mechanics is, we can be absolutely sure it's going to feel weird and be completely counterintuitive to the human brain. I'm close to them now. No copy assumption. No physical process can copy observers or create subjectively indistinguishable observers. This can easily be refuted with a cloning Gedanken experiment mentioned, earlier. So is Everett's interpretation falsifiable? The best way to test the theory is, of course, not to speculate, but to study quantum mechanics more. Physicists are trying to figure out different ways to test the theory. One quite practical example is that we should try to build quantum computers, which is a kind of machine which takes advantage of parallel computation, effectively using these parallel worlds. If we try to build them, and millions of dollars are spent right now on trying to develop quantum computers, and if it fails because we find that the basic equation of quantum mechanics is wrong, then Everett's interpretation would be falsified. But if they succeed and they can calculate something in 5 minutes that would take longer than the age of the universe for a normal computer, that would force more scientists to take Everett's interpretation more seriously. Now I would like to quote Richard Feynman's answer to the assumption that the universe must be such that we like it. Then there is the kind of thing that you don't understand. It means I cannot believe it. It's too crazy. It's the kind of thing I'm not going to accept it. The other part, well, this kind, I hope you come along with me. You have to accept it, because it's the way nature works. If you want to know the way nature works, we looked at it carefully. Look at it. That's the way it looks. You don't like it? Go somewhere else, to another universe where the rules are simpler. So if we take quantum mechanics seriously and accept that the wave function never collapses, only different parts of reality decoheres, what would that mean? It would mean that all kinds of crazy things. It would mean all kinds of crazy things. In some parallel branch of our universe, Hitler won World War II. In some branch, you were never born. And in some branch of our universe, believe it or not, Donald Trump is the 45th president of the United States of America. Okay, finished. Hello.
Well, thank you very much for that presentation. I'm trying to think words. I tried making some notes during it, and there's a couple of things which cropped up for me. I'll try and understand my notes. When you come to the human brain at the end of your talk, I think I tentatively disagree on the ground that the human brain has changed notably, according to archaeologists and historians, at least twice over a period of 100,000 years. And obviously it changed before that because we changed from our common ancestors. We're not Neanderthals, if you see what I mean. Neanderthals had their way of thinking and we have ours. So that would be one comment regarding brains and being able to understand your presentation and the universe. Another thing that
I was sidetracked by this, with the minds of broadcast. Well, first you say that the brain has, I mean, even if the brain has changed since the savannah, I mean,
I'm trying to progress.
There is no evolutionary pressures that has made us just to understand quantum mechanics. We're only adapted to the environment that was necessary for our ancestors to survive.
Past the environment. The first change was, I think it was the incredible human journey. It was described as the first fundamental change was the ability to understand the joke. For example, if it wasn't the Incredible Journey, it was another program, but the presentator said if you were telling a joke about a mammoth walks into a room, the group of Neanderthals wouldn't understand it. They'd say, well, yes, well, a mammoth walks into a room, so what? But the modern human could start to see the joke.
Yeah, but a group of Germans wouldn't understand it either.
So Germans are very good on fart jokes. I think that's a red herring.
No, I'm joking. That's not not the point. But
the point is, the brain changed in the way it actually processes and understands the humor, and that was actually a physical brain change.
Understanding humor.
100,000 years.
Understanding humor, I can see the point of it. Or like understanding difficult social things.
440,
but that's no
60.
But that's no adaptation to understanding the very large, the very fast, the very cold, the very hot, the very small, and things like that. We're only adapted to our kind of middle world. Even when it comes to social things, yes, I agree. One of the main reasons for why we are so intelligent is probably because we had to understand complex social environments. But that's no adaptation to understand quantum mechanics.
No, but I'm saying the brain has changed. There's no reason to say tentatively it might not change yet again to understand the quantum mechanics. You're saying we now can't understand. In the future, we might well be able to understand it because
no. I'm not saying. I'm saying we can understand it, yes, not intuitively.
No, I'm saying that we might be able to understand it intuitively. We just haven't evolved to that state yet. There's a possibility.
You can say like this. Do you remember the first time you heard about Einstein's theory, for example? When physicists first heard it, it was completely counterintuitive, and people didn't take it seriously because it was so counterintuitive. But then we have tested it so many times, so after a while, you see, okay, actually it works. And then you kind of make these pictures, as I showed 2 shows ago, about like how it creates ripples in space-time, although it doesn't really look like that. You see what I'm saying? So it's completely counterintuitive, but we are forced to adapt our intuition to it. So I think you can do the same with quantum mechanics, just that it's a little bit harder. I think Stop will say something.
Yeah, okay, let's stop, please. Maybe he doesn't want to say anything.
No, oh shit. I'm experimenting because I got this headset and it's not a normal one. It is a Bluetooth headset and it's got a microphone, and I'm experimenting with the range, doing all sorts of things. And I didn't know that I had inadvertently unmuted myself.
Okay.
Yeah.
Well, I'm just talking about it's a possibility that it might change. What you think? What we're thinking now is what we're thinking now as far as understanding things, but it may become intuitive because we have had these evolutionary leaps. I think it's a bit presumptuous to assume that we will never understand intuitively.
No,
things.
I'm not saying that we won't never understand. We can make up pictures to understand it, but what we should expect is that the further we reach in science, the less intuitive the things we're going to discover going to become, because we go farther and farther away from the environment that we evolved in.
Maybe.
So,
Yeah, but hang on. I've got one thing here. I realized that kids today learn like 5 times more than what I learned in school when I was in school. The same way that I learned 5 times more than what my dad learned at school. But the brains are more or less the same. So I think what is happening is that there is more knowledge, and there's more, well, theoretical knowledge that is being processed by the brain, which was not used 100 or 200 years ago. I don't think the brains have evolved within the last 200 years.
yeah, that's true. The same thing with like IQ. The IQ has risen enormously since the last 100 years, not because our brains is better. We may be, but it's just that we're doing other things. We're doing things that are more related to IQ.
Exactly. Yeah.
So
what I'm saying though is, if you're looking at, say, historical figures of the past, your Galileos, they were like a 1 in a billion people. But what if they became 100,000 Galileos all born at the same time?
That's what we have today.
Yeah, exactly. That's what we have today. Or actually, we have more. Most scientists that have ever lived are alive today.
Yes, but they are scientists trained by knowledge. Galileo didn't have the knowledge base. He wasn't standing on the shoulders of giants. He was the giant.
Yeah.
He was exceptional.
Yeah, it's always harder
the 1 in a million.
It's
But
always
what if
harder
he
to.
becomes the normal? Would that not signify a quantum leap in brain evolution, where Galileo has become the normal rather than something we have to train? And
No, it's not an evolutionary process, because if you want an evolutionary process, you need an evolutionary pressure. There are some like theories that.
No, you don't need an evolutionary pressure. Remember that evolution only works by the survival of the fittest.
Yeah, that's what I mean.
So the evolutionary bonus for Galileos would be the fact they are Galileos. Galileos are more likely to survive than fickoids.
Yeah.
Knowledge is power.
Although some people say the fickoids are taking over the world.
But I mean, the human brain can is plastic, and you can adapt it to many different environments. So like if we would like try to live like only surviving on agriculture like our ancestors did 200 years ago, we would die, or we would be completely useless, and vice versa. Those people will be completely useless doing programming language and things like that.
We know that the human brain, in the examples we have currently in the world, can be a broad spectrum from savants all the way through to people with learning disabilities.
Yeah. What happened to Rob? Where is him?
I don't know.
Because I did this presentation mainly for him.
Anyway, can I go on to my second point?
Yes.
My second point was regarding where does God play within Schrodinger's cat? Because it seemed to me Schrodinger's cat can only be in one of two states. If there's no God, it can't have an observer present.
No. It's not one of two states. It's indeterministic.
No, Schrodinger's cat can only be alive or dead if you don't know.
No. The condition is completely unknown. You don't know.
Exactly. You don't know. But God is there and omnipresent and sees. Therefore, the cat must either be alive or dead, and God would know.
What you're saying now is actually, there's actually some physicists that are making your argument, but this is making on the presumption that some kind of version of the Copenhagen interpretation is true. What I am saying is that whether you observe something or doesn't matter. The only thing that the observer does is it
verifies.
It creates decoherence. So what I'm saying is that the wave function never collapses. There is no observer collapses the wave function. The wave function continues. It's just that the different branches that the wave function creates decoheres from each other.
Abu, have you had the Professor Sean Carroll's explanation?
Yeah,
that's brilliant. I mean, it's so easy. Just use that.
Yeah,
I mean,
go and watch that. I can post that in the chat.
Yes, please do. I'll have a watch of it myself. And on your post, I'll link.
Oh, the rationalizers.
That talks about the cats.
Rationalizer, why can't you come on the show? We miss you.
Nah, anyway. he's gone all shy.
He can't have.
Okay, just to bring, but in a nutshell, the way that Professor Sean Carroll explains it is very easy, because he says if you are facing a specific direction and there's somebody using a skipping rope behind you, you know that the skipping rope, if you were to turn around, looks like a wave. But the moment, if you were to put like a reflective band of sellotape on one like random position on the rope, the moment you turn around and back again for half a millisecond, you will see that one piece of glowing piece of rope in a specific position. If you turn your back again, you don't see it. But the moment you see it, there it is. There's a particle in that position where you expect it. And this is the way that he explained it. This is the most easy way to understand it.
I didn't listen now. Sean Carroll believes in many world interpretation.
No. I'm talking about his explanation of how to understand, because GPZ was asking a question. And the way to understand it, the easiest way is just to understand what Sean Carroll was saying, and that is, if you are facing away from a skipping rope, it's being manipulated by two people, you know that it looks like a wave, and then the moment you look, you see a particle, it's no longer a wave, because you see this reflecting particle, and it's a position in the Hilbert space, whereas if you turn around, it's not.
Sean, I'm 100% sure Sean Carroll believes in Everett's interpretation, and Everett's interpretation says that the wave function continues. It's just that the different parts decoheres from
Yes, that's exactly what he says.
Yes.
Well, Sean Carroll just brought me to my third point, which was with Caliph talking about radio waves and only being able to pick up part of the spectrum, or in your case, stop the skipping rope when you turn around briefly, only having one point of it that you see. What you've described is the limitations of the tool that you use. In Stop's case, it's only being able to turn around and see microscopically one point fixed in a space of time. But if you had a camera that was videoing it, you'd see more of that dot moving up and down. Or if you had 100 radios all set to different dials of the channel, you would hear all the different broadcasting stations all at the same time. A terrible mess, but you'd still be able to do it. So it's only a matter of the tools that you have that help you interpret what you can get as data.
Yeah, but GP, you've got to, if you listen to a concert, it's different instruments playing at the same time.
If I listen to you, I'm actually hearing a completely different voice of Stott Spanning than I do when I'm listening